Good morning. Today is Friday, November 12th. The outline of the discussion is as follows. We'll discuss today matrix inversion, Cramer's rule, and also some economic applications. Now, these economic applications, class, are not yet referring to the input-output model because that will require a discussion on Yentief's inverse. So these economic applications is just how do we apply matrix inversion and Cramer's rule to economic analysis. Okay, so great. Now, in this case, we will need to get the inverse matrix of the 3 by 3 matrix. We can also call this one as matrix inversion. Now, I will propose to you some steps to follow in order to obtain the inverse of a matrix order 3. Now, take note, class, these are just the steps that I try to bring up into class. Because there are other ways that you can deal with a matrix inversion, but I think it's best to simplify it into a series of steps that you can all follow. Okay. Now we have this step one. So step one, class, we are just solving for the determinant. So we will form a matrix in which element aij, and then again, but before that, we solve for the determinant first. So why is there a need to solve for the determinant? It's a straightforward way to obtain its inverse. You see, class, if we have a determinant not equal to 0, then we are confident that we can arrive with an inverse. And at the same time, we know that we will arrive with a unique solution to that system of linear equations. So what will happen if the determinant is equal to 0? It means that the matrix is the linear system of equations is linearly dependent, and it's either you arrive with solution or you do not arrive with a solution at all. So again, before anything else, first solve for the determinant, and as you know, class, there are also ways which we discussed before on how to get the determinant. So it could be yung right and left, yung parang yung arrows, or you can also do Laplace expansion. So Laplace expansion, these are the methods that I say na I am expanding in the first row or I am expanding in the first column. Either way, I am just referring to how to get a determinant. Okay. The next thing to do is we will form a matrix of cofactors. But again, you already have a prior knowledge that in order to arrive with a matrix of cofactors, you will need to get first the minors. After the minors, you have the cofactors. Okay. Sorry. So that's what we that will do. There are sub process for this step. So again, step 2 is that we will be getting the corresponding cofactors from the original matrix, then to the minors, and then eventually to the forming a matrix of cofactors. Okay. Now, this is also one of the things that I discussed last time, wherein in transforming a minor class, we will need to attach the signs corresponding to the cofactor. So again, the assumption there is that it could be, for example, +1 multiplied to the minor, -1 multiplied to a minor. Okay, so again, these are the signs to guide you in transforming a minor to a cofactor. Okay, now the next step, class, is we will do matrix transposition. So when we say what we're doing here is we're transposing the matrix that we obtained in the second step, and the resulting matrix is known as the adjoint matrix of the original matrix. So what is happening here is that we are just only transposing this matrix of cofactors, and then we can call it or we label it as the adjoint. Okay, so again, when I refer as adjoint matrix, class, I am referring to the transpose of the matrix of cofactors. Okay, and again, we can also denote that one as ADJ, capital A. Now, the key here in this process is to have some labels or to designate these guides again to help you with the analysis. Okay, now Although it's okay naman class that we will just use C sub T, C superscript T there. But again, it's also good that we just call that one as a joint matrix. Okay. Then the next thing to do to get the inverse of a 3 by 3 matrix is yeah, once we obtain the adjoint, we divide each of its element by 1 over A here, and the resulting matrix is the inverse matrix. Now, take note, class, that this is what that the inverse is just equal to 1 over A. Now, we're not getting any absolute value here. We state it as is. This is how we write the inverse. This is how we write. This is how just we write the determinant. Okay. So again, when you have the inverse already, multiply it to the scalar. So this becomes the scalar. That is 1 over A multiplied to every element here, C11 multiplied to C21, 1 over A multiplied to C31, and also you do the rest for the other elements. Okay, so remember class that an inverse is just equal to, again, the ratio 1 over determinant multiplied to the cofactors. Okay, yeah, multiplied to the adjoint. Okay, so see, okay. Now let's have an example class and apply this process into an actual original matrix. Okay, so example number 1, we find the inverse of the matrix A below. So again, let's also take into practice that we know the symbol for that, and we also so that we can just later on do some symbols when writing matrices. Okay, so suppose we're looking for the inverse of this original matrix. The matrix, as you can see, is a 3 by 3 or order 3, and it has the elements 1, 2, 3, 0, 0, 1, negative 1, and 1, 2, and 1. Okay. Now, this again, the first step that I propose is to obtain a determinant by Laplace expansion. So the reason for this one is if I get a 0 for a determinant class, I can just stop there. And because I know already that I will not be getting an inverse. So if you have a determinant not equal to 0, you can go ahead and do the process. So for step 1 class, getting determinant, I just use the Laplace expansion method because again, later on I will just be using, I will need to get the matrix of minors and cofactors. So in that case, I am expanding, let's M11, M12, and M13. So that is, I'm expanding in the first row, okay? So remember class, this is how we did it last time. So M11 here, okay? So that's, this is M11, this is M12, and this is M13. So just a review, M11 is, again, or getting the minor, it's getting the submatrix. So deleting this column, deleting this row, and we'll end up with this matrix, 2 by 2 matrix here, which we call as M11. Okay, you do the same for M12, you also do the same for M13. The next thing to do is to get the determinant of these 2 by 2 matrix, and so you end up with 3, 1, and negative 1. Okay, so again, in the case for a minor 1, 1 class, as you can see here, this is coming from this matrix here, which is a submatrix from the original matrix. So that's 1, 1, negative 1, and 2. So that's 1, 1, negative 1, and 2. Getting the determinant of a 2 by 2 matrix requires you to get the intersection of the elements. Example, that's 1 times 1 minus negative 1 times 2. That's equal to positive 3. Again, and the same goes for the other two. Getting the determinant means that you need to be consistent with, again, with the coefficients that you will be using. Because I am using or expanding in the first row class, then therefore my coefficients and also my cofactors would also be in the first row. Okay, so again, this is quite the format for getting determinant using Laplace expansion. Multiply the coefficient times the cofactor. So that's A11. A11 is 1 here. So let me just delete this one here. Okay, so A11, that's 1. Multiply to the cofactor, C11. Now, before going to this one class, let me also go back to this one here. So this is, again, minor and cofactor. So when you have a cofactor class, you will need to transform that one. When I say transform, it means you are attaching the signs already. So for a C11, that's 1 plus 1, so that's even, so that's a positive 3. Or you can do it like this. Because this is even plus 1 plus 1, you will need to multiply this minor to a positive 1. And that's why the answer is 3 for cofactor 1, 1. For C12 plus, again, C12 is 2 plus 3, so that's an odd. Odd means negative 1, so that's negative 1 times 1, which is our minor 1, 2 here, and this is negative 1. Okay, let me just also C13, that is 3 plus 4, so that's positive 1. Multiply it to the negative 1, which is equal to negative 1. So again, these are the signs that I'm talking about. These are the signs for the cofactors. These are your minors right here. Again, these are the signs for your cofactors. These are also these are also your minors right here. You get the product of the two, and then it will be equal to these numbers right here. Okay. The next thing to do here, again, you multiply the coefficients and the cofactors that we have derived here, and you'll get a determinant that is equal to negative 2. Now, because your determinant is equal to negative 2 here, class, you are already, again, it's an indicator. That's a signal for you to carry on with the process, because you'll know that you'll get an inverse eventually. Okay. So again, there's really nothing new in this slide. You already know how to obtain a determinant. You also know what Laplace expansion is. Okay. So now, let me also guide you through this slide here, because it appears that there's a lot of content in the slides. But let's start first with what step 2 is. So step 2, class, is we will need to form a matrix of cofactors. Now, there are a series of sub-processes here, because again, obtaining cofactors would mean obtaining the minors first. Okay, so how do you get a minor? Okay, so I usually write this one on the side just to guide me, class, in answering. So if this is our original matrix, you get first the minors, and you have a matrix for the minors. Okay, so how did we arrive from this original matrix? This is our guide with what M11 is, M12, M13, or these are just the placement or locations of your minors. Example, I'll use this one as an example to get the elements or to get the matrix for the minors. Okay, so M11, we know M11 is around this part here. Again, so that's remember IJ, class, I is row, J is column. So M11 here is around this part. So that's 1 here for the original matrix. Delete this row. Okay, let me just do it this way, right? And also show. Okay, right. So again, delete this column. Let me correct that one. Delete this column and also delete some row here. Okay, let me just also. All right. Okay. So M11 states that delete this column, delete this row, you'll end up with 1, negative 1, 2, and 1. Let's also do M21 plus or minor 21. So minor 21 is this part here. Just do it like this. Okay. And you'll end up with 2, 3, 2, and 1. 2, 3, and 2, and 1. You also get M31. So M31 is this part right here. So that would be 1 in this exercise. So that would be 2, 3, 1, and negative 1. Okay, you do the same for the rest, class. Okay, the key about minors is that you just need to delete some rows and columns depending on the placement of the coefficients. Okay, so what happens next for a minor is you get the determinant of that 2 by you get the 2 by 2 determinant of that you get the determinant of that 2 by 2 matrix. Example, you have in this case 1 by 1, in this case, this is 1 times 1 minus negative 1 times 2. The answer is equal to 3. 2 times 1 minus 3 times 2. So that's negative 4. And you also do the same for the other minors. Okay, so again, there is really nothing new in this part of the discussion right here. All we did was just to coagulate, just put all together what we have learned so far. After getting all the minors class, you will be or can be able to build a matrix for the minors. Now I mentioned earlier that it really pays to it really helps class that you need to have some labels here to have an understanding. So in that case, M here would signal as not the original matrix, but just the matrix for the minors. Okay. Now, if you're done with the minors class, you can already go ahead with the cofactors. Okay. So this part of the slide, I already indicate how do we transform a matrix of minors, to a matrix of cofactors. So as you can see here, we have our original matrix. Again, I just put that one on the side just to guide me. But anyway, it's not, this cannot, will not use this one in getting cofactors. Okay. So again, very specific to this slide. So for minors class, this was our minors a while ago. And I attached the signs already. So these are again the signs that we mentioned last time. For example, by the way, class, I am not doing any matrix multiplication here. What I'm only doing is I am just attaching the signs. Okay. So again, how do we transform a matrix to a cofactor? No, a minor to a cofactor. Example, 3 times positive 1, 3. 1 times negative 1, negative 1. Negative 1 times positive 1, negative 1. And also do the rest of the rows. Okay, and that's how you transform a minor to two cofactors. Okay, now if you're done doing that class, step 3 requires na we will transpose cofactors. Now again, matrix transposition tells us that if it is an m by n, okay, so in general class, if you have a matrix equal to n by n, okay, your transposition is equal to n. The transposition would be equal to this one. Okay, it will now become n by m. Okay, so how to transform this or how to transpose these cofactors? First row would be first column. Second row would be second column. Example. This is our, as you already know, class, I always want to start by rows. So row here would be the first column on the adjoint matrix. So first row, 3, negative 1, negative 1 would be our first column. Second row would be the second column, 4, negative 2, 0. So that's 4, negative 2, 0. Again, this is a column here, but this is a row here. Third row, negative 5, 1, and 1 would be our third column on the adjoint matrix. Again, the adjoint matrix class by definition, it is just the transpose of your cofactors. Now, before I proceed to this to the next part of the steps class or the process, are there questions for step 1, 2, and 3? I actually can't review if someone is messaging me or not. But again, I just unmute yourself if ever you have a question. Okay. So I think there is no question. I'll proceed to the next step. So step 4. So step 4 class, we divide each element of the adjoint matrix by the ratio 1 over determinant to obtain the inverse. Okay. So again, when you have inverse kasi class, you can just follow this general, let me just correct this one. So that's AX equal to 1 over A, and then inverse 1 over A, and adjoint matrix. Okay, so multiplied by the adjoint matrix. Okay. All right, so the inverse, in order to get the inverse of the original matrix A here, you will need to multiply that one. So that's 1. Okay, for a while class. I'll correct myself, plus I think right. Good. So multiply each element of the adjacent matrix by 1 over A to obtain the inverse, So that would be 1 over 1 over negative 2. Okay, so again, for step 4, we multiply the we multiply 1 over 2 here and multiply 1 over the determinant to every element of the adjoint matrix. So in this case, we will be treating 1 over negative 2 here as a scalar. So again, scalar has its peculiarities. It can be multiplied to every element of the matrix. So 1 over negative 2 multiplied by 3. So that would be negative 3 over 2 here. 1 over negative 2 multiplied to the element 4, and then you'll have negative 2. You'll also need to do the same for the rest of the elements. And so you will end up with what we call an inverse of A. Okay. So again, for steps 1 to 4 class in this process, this is how you can obtain an inverse. But it does not stop from there because you will need to do other things before arriving to the the unknowns or to the solved solution. Okay, so after getting an inverse class, what you need to do is to verify. Now, bakit ba kinakailangan natin to verify? Again, before kasi going to the actual value of x, I think it's also best to verify if the inverse that you got is also correct. Now, one thing to verify, the way to verify the values is to multiply it to the original matrix. And if it yields to an identity matrix class, you're certain now that your inverse is really the inverse of A. Okay. So in this case, you can do either this side. You can also either do this side. So in this case, what I did was to do this side as well already. I did this part of the verification. But either way, class, either you do this or you do that, you will end up with an identity matrix. Okay, so again, verify here. Okay. Okay, so baka yung sinabi ko kanina on my class that I'm doing this part. But anyway, let me just go back. What I'm actually doing is this part. Okay, so let me go back to that. Okay, so again, in all right here. Okay, so right. So what I'm doing here is verifying it the inverse times the original matrix. So this is the inverse a while ago. This is this matrix right here is our inverse, and then multiply it to the original matrix, which is this one here. Again, this is what we do. What you're doing already is what we call matrix multiplication, and if our inverse is correct, it should be equal to the identity matrix, which is one diagonal, 0 everywhere. Here's an example class on how to obtain 1 here. So just a review on matrix multiplication, this is how we're doing it. Okay, so remember, I'm quite comfortable with row, column. So what I did was that first row, first column, and then you'll arrive with 1. Okay, how did we do that? So that's negative 3 over 2 multiplied by 1 plus negative 2 multiplied by 0 plus 5 over 2 multiplied by 1, and your answer should be equal to 1. Okay? I am completing the answer for this row. So that's, let's go to that. So that's negative 3 over 2 times 2, negative 2 times 1. So here's the guide. Plus 5 over 2 times 2, the answer is 0. For this 0 right here, okay, so that's the answer for this one here. So in this case, how did we obtain for the 0 here? So that's negative 3 over 2 times 3 plus negative 2 times negative 1 plus 5 over 2 times negative times 1, and we got an answer which is equal to 0. So that is how we solve, that's how we do matrix multiplication, okay? So again, class, as we have seen here, we have verified that the inverse that we got is really the inverse of A. Okay. Now, what is the next thing to do? Remember, class, that this was our first step earlier. Again, we have a system of linear equations. In order to get the value of the unknown, or x, we will need to multiply that one to the inverse times the constant. Again, we are first given with this linear system of equations. What we are solving is the endogenous variable, or what we're solving is what we're solving for is x. So x here, or is only solved by multiplying the inverse times the constant. So in this case, if we have if this is our unknowns class, this is our inverse, and this is our constants. So again, what we did here, we are doing matrix multiplication as well. So matrix multiplication tells us that we are still conformable with, we still do not violate the dimensional requirement, which means that the lead matrix of the column dimension of the lead matrix should be equal to the row dimension of the lag matrix. So for example, 3 should be equal to 3. The product should be equal to 3 by 1. Again, dimensional requirement states that these three, this one should be equal to 3, and the product would be a 3 by 1. Okay, so carry on to the process of matrix multiplication. So that's row, column, row, column. So that's 3, negative 3 over 2 times d1, plus negative 2 times d2, plus 5 over 2 times d3, and you have an answer. We do the same for the rest of the elements, and the solution value class, again, we put already a star there, so, or an asterisk or star, but again, this indicates that we already have a solved solution. We have a solved value for the three unknowns. So for x sub 1 star, your answer is this. X sub 2 star, your answer is this. X sub 3 star, your answer is this. So that is what we call matrix inversion class, and we use that method to arrive with a value of x. Before I go to the Cramer's rule, are there questions, class, that you want me to, are there questions or some a slide there that you want me to go back and discuss and clarify? Can move forward to Cramer's rule. Okay. Now, for Cramer's rule class, it is a method for solving for n unknowns, variables, and a system of n equations. And again, it is an alternative to the inverse matrix method. So in this case, if you're given a system of linear equations, you can either do matrix inversion, or also you can do Cramer's rule. So now let's also recall some of the things that we have already noted last time. So recall that the system of equation is again written as this way here. So we're first given with a linear system of equation, ax is equal to b here. And then what we did was we got the inverse, and the inverse is again, the inverse of the multiplying the inverse to the original matrix will lead to the identity matrix, which is equal to this one. And therefore, class, solving for x would mean that you will need to get the inverse and multiply it to the to a constant, or to the constant of that equation. So also it would be help to do some labeling, class. So again, this would be our x star, meaning our solved solution. Okay. Now, generally, class, as you can also remember, this is the general format when we did something like this. Okay, again, generally, if you put this in a more general manner, class, it will look something like this. Okay, so again, this is our unknowns, and this is our inverse right here. And we also have our constants. Again, generally, getting the values for these unknowns would mean that this is our inverse right here, and this is our constants. Okay, so in that case, notice class that the solution value specifically for x sub 1 is just the ratio is just 1 over the determinant multiplied by the constant, which is the sum of the product of the constant and then the cofactor here, plus again it's also a constant times the cofactor, constant and cofactor. So which means to say, class, that the logic that in the logic of Cramer's rule is it is just the evaluation of a matrix derived determinant, and then we will need to replace it with a constant here, which is our column vector. Okay, so I think this would be best explained if we have an example. So let's start with this one, class. Okay, suppose that you're given the system linear of equations here, and then you already know that we can solve the values for x1, x2, and x3 by using elimination or substitution methods. However, you can, because you already have a knowledge of what matrix algebra is, you can just do Cramer's rule to answer the values for x sub 1, x sub 2, and also x sub 3. Now, in this case, class, what we will do first as an approach to this analysis is transform these linear equations to matrix form. So when I say matrix form, that is rewriting it in a compact way, ax is equal to d. Okay, so again, a here would be our set of coefficients. So that's 2, 4, negative 1, 1, negative 3, 2, 6, 5, and 1. Again, how did we arrive at the matrix of coefficients here? These are just your these are just your coefficients from again, remember coefficients, class, or definition of what coefficients is. So it's attached to a variable. Okay, so that's 2, 4, negative 1, 1, negative 3, 2, 6, 5, and 1. Okay, so that's our matrix of coefficients. We also have our matrix for unknowns or something, or these are what we are looking for in this problem right here. So this is what we are trying to solve. Okay, so we're solving for the values x1, x2, and x3. And we also have our constants. So when we see constants, it's usually on the right side, but I think I don't want to put it that way. But again, when we see constant, there's something that doesn't change, that is, we take it as a given, something that we do not solve at all. Okay, so these are exogenous to your model here. So our vector of constants is equal to 15, negative 5, and 28. Okay, and so this is how we rewrite the system of linear equations into the matrix format. Now, the next thing to do, class, just like what I mentioned earlier, is to get the determinant first, because doing so would save you a lot of time. So if you get a value that is equal to 0, stop right there. You know that's you will not end up with a unique solution. However, if your determinant is again not equal to 0, go ahead, do the process, because you know that that solution would be unique. Okay, so in this case, this is just the Laplace expansion. As you can see, I am expanding in the first column or along the first column. Okay. This one I already did not incorporate the. I did not do in detail yung minors and cofactors, but I think I already understood, class, that what I'm using here is just the minors and cofactors. Okay. Now, for Cramer's rule, class, there's only one process that you will need to do for the rest of the for solving x sub 1, x2, and x3, because again, it's just the same logic all throughout. Now we are getting a solution for x sub 1 here. So the solution for x sub 1 is just equal to the determinant of the new matrix A1 divided by the determinant of the original matrix. So again, it is just the ratio ratio of the evaluation of the new matrix over to the determinant of the original matrix. Okay, so again, this was our given. It's best to see to attach this one to the side just for guidelines. So in this case, our original matrix here, and we also have our constant. So yung sinabi ko kanina is that we will substitute this one to to form a new matrix. Okay, so A1. So A1 is a new matrix here. So the first column class is our constant. So we substitute this constant to the first column and the rest of the elements as is. Again, this was our original matrix. We are now forming a new matrix and we call that one A sub 1. A sub 1 class is column. Okay, so we substitute the column vector, the constant vector to the first column to the new matrix, and the rest of the the rest of the elements are just as is. Okay, so again, we have the same second column. We also have the same third column. The next thing to do is you get the determinant of that new matrix. So the matrix of A sub 1 plus is equal to -10. Again, this solving for x sub 1 is just getting the determinant of the new matrix and the determinant of the original matrix. So getting the determinant of A1 is equal to -10. You get the ratio class. Solve x1 here is equal to, let me just write down an indication here that is our solved problem. So x sub 1 star is equal to -10 over -5. The answer is 2. Your value for x sub 1 is equal to 2. Again, saan ang galing yung -10? Ito yung determinant ng new matrix. Saan ang galing yung -5? Ito yung determinant ng original matrix. Okay? Now, let's move forward for number 2, solution for x sub 2. Again, there are 3 unknowns here. So again, you'll find it comfortable kasi you're just using the same process anyway. So for x sub 2, again, you need to get the determinant for the new matrix divided by the original matrix. We have here our original matrix. We need to transform. We need to write again a new matrix or form a new matrix. So that we will call that one as A sub 2. Then again, substitute this one to the second column. Again, this would be an indicator class on what to substitute. So if it's 2 class, then you're referring to the second column. Okay, so that's 216 original matrix here as is. Second column would be the constant because again, we're evaluating the solution for x sub 2. Third column would be the original, also from original matrix, and then as is din siya. The next thing to do is we get the determinant of that new form matrix, and the determinant is equal to -15. So kaya class in their review, yung mga questions is focused on determinant because again, it's an exercise for you for the Cramer's rule, most especially. Okay, so to get the value for x sub 2 star, you will need to get again the ratio of determinants from the original and from the new matrix and to the original matrix. So saan ang galing yung -15? Ito, from the determinant of the form matrix. Saan ang galing yung -5? Ito din yung determinant ng original matrix, and you have a solved value which is equal to 3. Now, I think class, ito din for the solution for x sub 3. Again, the same process, but you'll only have to take note on what column you are evaluating. So for example, if we're forming A3 here, 3 is, again, we're evaluating the third column. So you will need to substitute it in the third column as well. You do the same exercise, you get a determinant for that new form matrix, and you get the ratio, and then your answer would be equal to 1. Now, before I proceed to the next slides, question? Okay, now in that case, class, summarizing the values for so summarizing the values that we got, we can just we can write it this way. So again, we first started with a system of linear equations written in this way. Then we do matrix algebra using Cramer's rule. Then we can summarize the values for the unknowns, which is equal to the column vector 2, 3, and 1. Okay, so later on, if I would be asking you solve the values for this specific system of linear equations, you can write it this way. But then again, it would be different if I ask you, do an economic analysis of this part here. Okay, so it's also equally different. Okay, so that is how we use matrix. That's how we use matrix inversion, and that's also how we use Cramer's rule. Now, you can already compare class which method you are comfortable with, especially that when you're getting the values for a specific value for a system of equations. So either you can do Cramer's rule, or you can also verify using matrix inversion. So if your values are correct, you will always arrive with the same result. Okay. So I have one example here. I actually prepared two examples here, class, but I think I'll just focus first on the second one and on the first one, and then I will go back to the second one next meeting. Okay, so just siguro to give you an economic application on how do we use matrix inversion when dealing with some economic analysis. Okay, so for in this example, I am using matrix inversion. So the case here is that we have these two equations and we're solving for an equilibrium condition for these two substitute goods. So we're looking for the prices of good one. We're also looking for the prices of good two. Now, again, you can easily, because these two equations are linear, you can just easily go ahead and do substitution or elimination methods. But of course, because the topic requires us to do matrix inversion, we can also do that. Okay. Now, let me put this one on the side. Okay. So the first thing to do is, again, transform it into matrix form, that is EF equal to D. So we need to write a matrix of coefficient, a matrix of variables, and also the column, the constant matrix. So we're writing so that's 5, -2, -1, and 8. We also have what we are solving, what we're looking for, the equilibrium price for both goods. And we also have a column vector which are constant, something that we do not solve. Okay, so that's 15 and 16. Now, solving for a determinant for a 2 by 2 class is not a problem because again, it is just the intersection of these elements and also these elements here. So the determinant is equal to 38. So again, it is non-singular, which means we will have an inverse later on. Okay. The next thing that we did was to get the cofactors. So again, this is already with the assumption that we're done doing minors here. And so the set of cofactors is equal to also to this 2 by 2, composing of elements e to 1 and also to 5. The next thing that we did is to get the to get the adjoint of the matrix of cofactors. So when we see adjoint class, it is just the same as getting the transpose of the cofactors. So again, our first row here would be our first column. Our second row would be our second column, and we have an adjoint already. The next thing to do, if there's no question, is that we can go ahead, use this adjoint matrix to get the inverse. Getting the inverse would mean we have to divide, divide it with we divide it with the determinant. So in this case, multiply the coefficients into the scalar, which is 1 over 38. So saan na galing yung 1? So it is a given. 38 is your determinant. So as a given, that's 1 over 8. 1 over 38 acts like a scalar, or actually it's a scalar class. And then you will have to multiply that to every element of the matrix. So that's 1 over 38 multiplied to 8. 1 over 38 multiplied to 2, 1 over 38, to also to 1 and 5. And you will end up with this one. Now, this is what we call an inverse of the matrix. Now, in terms of solving the obtaining the inverse class, we are actually done with just getting the inverse. But you all know this is a series of steps in getting the getting the x or getting the unknowns or variables. So we do not stop there. The next thing that we will do is again, remember this part here, okay? In order to get the solved value of x star, multiply the inverse to that of the constant. So in that case, that's what we did. This is our inverse class, okay? So let me just also add to this one. So this should be what are we looking for in this exercise? We're looking for P1, the prices of good one. So P1, P1. So P1 is equal, so what we're solving for is P1 and P2. Okay, let me just go ahead to that. The adjoint class is again, the first row would be the first column. The second row will be the second column. So in terms of placement, it should be uh, a the first row. Our first row here should be our first column. Second row should be our second column. So that would be the adjoint because again, we're doing transpose. It's not 2, 8. It's not 2, 8 kasi yeah, hindi. Okay. I think you mentioned, I think remember class, remember yung isang material na we attached the signs already. Actually, this is just a similar shortcut to that. Okay, so kaya ganito siya. Okay, so yun. Alright. So now what happens after is that we are multiplying, we're just following this formula class, then we're getting the inverse and also the constant. Okay, so that's or yeah, we're multiplying the inverse and the constant. So that is uh, again, that is row, column, row, column. So again, I think I already, so that's 4 over 19 times 15 plus 1 over 19 times 16, and you'll end up with this number right here. So in that case, class, we will have a values for P1 and P2. P1 star is equal to 4. P2 star is equal to 2.5. So just this, our economic analysis in this case would mean that if the price of good 1 rises, the quantity of good 2 would decrease. Okay? Because again, they are called substitutes. If tataas yung presyo ng isa, bababa yung quantity demand ng isang good. Okay? Alright, so that's how we will be doing it for matrix inversion. Now, for example 2 class, we'll tackle that one next time. This time, we're using Cramer's rule. Okay, so as you can see, this does not only apply to microeconomic analysis, but also applies to macroeconomic analysis as well. Okay, so do we have a question about specifically for this example? Okay, so I'll end up my recording to this part. Okay, so